Hi, I'm Madison Bellamy, and welcome to Module 1 of Critical Thinking, where we will be using inductive and deductive reasoning to solve word problems. Let's jump right into it. Alright, so our first problem here says place the digits 8, 10, 11, 12, and 13 in the circles to make the sums across and vertically equal to 31, which we'll see here in a second what that looks like in a diagram. Part A says, is there more than one answer to the puzzle? And part B, show all possible combinations of numbers to prove how many combinations exist which meet the rule of 31. Okay, so we are going to use a system of guess and check here. Vertically and horizontally, all of our numbers have to equal 31. So let's see what that looks like in a diagram. So we're just going to randomly place the letters here. Not letters, numbers. All right, so we have 10 in the middle, 13, 8, and our last two numbers, 11 and 12. Okay, so let's add up our numbers horizontally. 13 and 10 is equal to 23, plus 8 is equal to 31. So right off the bat, horizontally, we have 31. So that's great. Vertically, we have 10 plus 11, which is 23, and then plus 10, which is 33. So we have 31 and 33. They do not equal 31. So for this next graph, we're going to keep 13, 10, and 8 together because we already know that they equal 31. So we're going to try and keep those together, but switch them around this time. 13, 8, and 10, yes. And then, of course, we have our 11 and our 12. Okay, so 8, 13, 10, we already know that that is equal to 31. So now we have a different combination of numbers in the middle, 12, 13, and 11. So 12 plus 13 is equal to 25, plus 11, which is equal to 36. So again, vertically, we are not equal to 31. So we need to keep going with our trial of guess and check. So we're going to keep our 18, 13, and 10 together because we already know that that equals 31, and we're going to switch them around one more time. All right, we have our 13, 8, and 10, and then our 11 and 12. All right, horizontally 31, we got that. Vertically, we have 12, 8, and 11. 12 plus 8 is equal to 20, and 8 plus and 11 plus 20 is equal to 31. So we have found our combination that is equal to 31 horizontally and 31 vertically. All right, so our next part of the question is asking us, are there any more combinations that equal 31 horizontally and vertically? Well, we saw from these other graphs here that no other combination is going to work for us that we haven't already tried. So, of course, we could switch up the 13 and 10, switch those around in the 12 and 11, or have the 12 and 11 sit horizontally while the 13 and 10 sit vertically, as we can see here. All right, so that answers our question. 12, 8, and 11, 13, 8, and 10 is our answer for vertically and horizontally to answer if that is equal to 31. And part B, is there any other combination? And we see that we can flip them around, but really no other combinations would work other than that. Okay, question 2. 9 square tiles are laid out on a table so that they may make a solid pattern. Each tile must touch at least one other tile along an entire edge. So if one tile is here, another tile has to be touching it completely on another edge. The squares all have a side length of 1. So good, that's a good thing to measure by. We have a whole number. Part A says sketch all possible figures which can be formed and calculate the perimeters of each figures that can be formed. The perimeter being the distance around the figure. Part B says which figure has the least perimeter and which has the greatest perimeter. Fortunately, we can find out B along the way as we add up all the perimeters as we go. That would just be the easiest way to do it. All right, so our first method of madness would be to just line them up side by side. They all are touching each other. So let's go ahead and try that. All right, so all of our cubes are lined up side by side. They're all touching each other. One side length is at least touching one other one. So they're 9 blocks. So we have 9 going down this side, 9 going down the left, so that's 18. And then we have our top, which is 1, and our bottom, which is 1. So that would 1 plus 1 equals 2, 2 plus 18 equals 20, which is our perimeter. All right, so our next would be to form a 3 by 3 cube. We have 3 on all sides because they're all equal to 1. 3 on this side, 3 on this side. So we have 4 sides. So 3 times 4, our perimeter is equal to 12 because all of our sides add up to 12. And in our next figure, all of our sides are touching at least one other tile along one side length. And this perimeter is equal to 18. We have 1, 2, 3, 4, 5, 6 going down this side. 2, that is equal to 8, 9, 10, 11, 12, because there's 2 right here. 13, and then we have 14, 15, 16, 17, and 18. So for our next figure, this perimeter is equal to 16. So we have 3 along the top, 4, 5, 6, 7, 8, and this is a symmetrical figure if we cut it diagonally. So 8 on one side, 8 on the other, and that is equal to 16. And for our last figure, we can get that PowerPoint toolbar out of the way. For our last figure, this perimeter is equal to 14. We have a 2 by 3 cube on the bottom, so that whole cube is going to be equal to that dang PowerPoint toolbar. 2 on one side, 2 on the other, 3 on the top, 3 on the bottom. So 6, 4, 5, 7, 8, and then 9, 10, 11, 12, 13, 14. Alrighty. So we have that. And we are, no, we have another part of this question. Okay. Part B asks which figure has the least perimeter and which has the greatest perimeter. And we can see out of all these that we have 12 and 20 to be our greatest and least perimeter. Okay. So, question 3 says, consider a new sequence of dot patterns below and complete parts A through C. So up top, they're just giving us some examples. This is a triangular pattern at the top. The zoom toolbar would go away. This is a triangular pattern at the top, so it's giving us the formula in that little cloud for the triangular number, which is the amount of dots that make up the triangle. So it's giving us the formula for that. And then we have a square diagram set up in the second example, and that is giving us the square number. So that is going to be down below. All right. So in our word problem we're working, it says consider a new sequence of dot patterns below and complete parts A through C. So these are our dot patterns. We have one dot here, and it seems we are working with pentagons. So we have pentagons. Okay, so here's our diagram up top. Let's just leave that there. Part A says draw the next 2 figures to continue the sequence of dot patterns in the box. Okay, so draw the next 2 figures to continue the sequence of dot patterns. Well, before we can draw the dot patterns, we have to establish a pattern first. So let's configure what is going on here for this pattern. So we have 1, 5, 12, and 22. So it's going from 1 to 5. So it seems that 1 would increase by 3. So 1 plus 3 is 4. And 1 plus 4 is equal to 5. So that seems to be our pattern here in the first one. So 1 plus 4 equals 5. So for the third, how we would get the third, this 12 here, 1 plus 4, add 1 plus 3 is equal to 4. plus add another 3 is equal to 7. 4 plus 7 equals 11, plus 1 is equal to 12. So we seem to be adding 3 each time, adding those sums together to get our pentagonal numbers. So let's see. We have our formulas, and the first 3 represent the 5, 12, and 22, those first 3 sequence of dot patterns. And the next 2 are going to be our sequence of dot patterns for the 2 figures we're going to draw. 1 plus 3 equals 4, plus 3 equals 7, plus 3 again equals 10, plus 3 again equals 13, which is total to 35. And we're just going to do that again for the second figure. Left off on 13, plus 3 again is 16. All of that summed up together is equal to 51. So this is our pattern for our figures. We're adding 3 each time, adding those sums together to get our figure number. Alright, and we would draw those. Our next pentagonal number is going to be equal to 35, as we see here. This is our last known drawn figure, 22. And then our next one will be 35, and our next one will be 51. So just do that. Alright, so that is what they're going to look like. We have our 22 pentagonal diagram in the center here, and we've added on our new dots to equal to 35. So we have 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 35. So we have that here. And again, same thing for the next one. We're going to add our pentagonal diagram into the middle of this one and add our new dots to get 51. Alright, so those are our next 2 drawn figures. In question B, it asks to list the sequence of numbers that correspond to the sequence of part A, which we've already done that. Here on the left here, we've taken our first number and we've added 3 each time to get our new number to add to the previous one. So 1 plus 3 is equal to 4, 1 plus 4 is equal to 5, and so on for the rest of our number figures. And I just want to note that the first sequence that we see here, that first equation that we see here, that is actually our second one, because that represents the second pentagonal number diagram, which is the number 5. We are not seeing the one for number 1, because so technically that is number 2. But that answers our question to part B. We're just going to leave that there because we have already done that in advance. Alright, part C. Add 4 more equations to the list below. These equations are suggested by part A and B. Okay, so again, we're just adding more equations. So it's giving us left off on 22, that pentagonal number, and we are going to add the next one. So we left off for 10 on this last equation here. So we would add the next 3, which would be 13. So 1 plus 4 plus 7 plus 13, and that would get our next number, and so on. So we see that here, we added 13 and we got 35. 13 plus 3 equals 16, add all of that together and we get 51. And so on for the next 2 equations. We add 3, got 19, add all of that together to get a sum of 70. Same thing with the next one. 19 plus 3 is equal to 22, which equals 92. So that would be our pentagonal numbers and our arithmetic numbers in our equations. Okay. And D says to observe that each pentagonal number is the sum of an arithmetic progression. So yes, that is true. We have our pentagonal numbers at the end, that is our total, and the arithmetic progression is our add 3 each time. Compute the 10th term in the arithmetic progression. So it's asking for the 10th number in our arithmetic progression. As we can see here, we left off on what number? 1, 2, 3, 4, 5, 6, 7, 8. So our last equation there left off on the 8th arithmetic progression. So since we have already calculated to 8, why not just go all the way to 10? That seems easier, but as we can see here, I already have the equation if we were needing to do the arithmetic progression of 50. Say that. We would need to use this equation because it's much easier than to draw it out. But since we've already left off on 8, it would be easier in this circumstance to just add from there. So our 8 arithmetic progression was 22. So we are going to add 3 to that to get our next arithmetic progression. And that is going to be 25. So we had 22, we added 3 to get our next arithmetic progression, and we got 25. So that is our 9th arithmetic progression. And it's asking us for the 10. So let's move on from there. We have our 9th, which is 25. We are going to add 3 more to get our 10th arithmetic progression, which is 28. So 28 is going to be the 10th term in our arithmetic progression. And that is represented by the nth term here. Okay, the last problem. And the last part to this word problem, part E. Show the formula for pentagonal numbers and calculate the 9th, 10th, and the nth terms. So our nth term is already represented here as the pentagonal number. This is the equation we would use again if we need to find the 50th term. So our nth would be n times 3 times n, which is a number, minus 1 divided by 2. So we would replace whatever number we are trying to calculate for a pentagonal number. We are going to replace the n with that number. So if we were trying to find the 12th pentagonal number, we would replace n with 12. But in this case, we are trying to find the 9th pentagonal number as the first one. So it's set out in this equation here. We are starting with our pentagonal number equation, and we are plugging in 9 for that n. So 9 times 3 times 9 minus 1 is divided by 2. So 3 times 9 minus 1, 3 times 9 is 27, minus 1 is 26. So we're going to do those parentheses first. Then we're going to multiply again, because it's just left to right, multiply again. 9 times 26 is equal to 234, and divided by 2 is equal to 117. And as we saw in that last slide, if you're paying attention, our total for our pentagonal number was 117 when we did our 9th arithmetic progression, but our 9th pentagonal number is 117. All right, so it is asking for the 10th pentagonal number as well. So we're just going to do the same thing that we did for the 9. We're going to plug in the 10 in place of the n. So we're starting out with our original equation. Always start out with your original equation. And plug in 10 for that n. So we have 10 plugged in the second row. And 3 times 10 minus 1 is equal to 29. 3 times 10 is 30, minus 1 is 29. Again, left to right, do our parentheses first. Multiplication. 10 times 29 is equal to 290, and divided by 2 is equal to 145. And again, if we check back on that last slide, we will see that our pentagonal number is total to be 145 if we just want to do check our work. All right, so let's move on to question 4. Okay. I'll just leave a box for that. Okay. The figures show an addition pyramid, let me see that below, in which each number is the sum of the 2 numbers immediately below. For each of the incomplete addition pyramids, show that the values in each square can be determined by forming and solving an equation in the unknown variable shown. So we're going to be forming equations here and solving that way, as it says in our word problem. This 4th pyramid here is a complete pyramid, just showing that there is progression in each level, that the box above is the sum of the boxes below. So 3 plus 5 equals 8, 5 plus 4 equals 9, and those 9 plus 8 together is equal to 17. So that's just our example box. So let's go ahead and take a look at our first addition pyramid. We have 2 blank boxes and X in place of a number in a box. So it would be fair to say that 7 plus 3 is equal to 10. So we can already establish that that box above is 10. So, but it wants us to establish an equation. So easily we could say, okay, 25 minus 10 is this number, and so and so. But it wants us to establish an equation. So it would be fair to say that 7 plus x is equal to 7 plus x plus 10 is equal to 25. So we're going to go ahead and set up that equation. 7 plus x plus 10 is equal to 25. If that PowerPoint toolbar would just go away. Okay, so we have our equation 7 plus x plus 10 is equal to 25. So we are going to use this equation in order to find out what x is first off, and then establish after that whatever x is plus 7 is going to be in the box above. So we solve for that equation. We're going to add our two whole numbers together, 7 and 10, to get 17. So we'll have 17 plus x. Then we are going to subtract 17 from both sides. So 17 from that side is going to be minus 17 from 25, and that is going to leave us with x is equal to 8. So now that we know that x is equal to 8, we can go ahead and see that 8 places that x there, and 8 plus 7 would be equal to 15. And if we wanted to check our work, we could say, okay, 15 is here, 10 is here, 15 plus 10 is equal to 25. So that is that for the first one. All right, so let's go ahead and look at the second equation. Addition pyramid. So we have y in place for a number in the center and two blank squares at the top. So to create an equation for this, the bottom row is going to be the sum of the top row. So it would be fair to say that 1 plus y is in the left-hand box here, 1 plus y. And it would be fair to say that y plus 2 is in this box here. And that 1 plus y plus 2 is equal to 15. So that's going to be our equation here. 1 plus y plus y plus 2 is equal to 15, because that is how we are going to establish our y. So let's do that first. We have our 1 plus y, our 2 plus y is equal to 15. That's our first equation. So we're going to go ahead and put our whole numbers together. 1 plus 2 equals 3, and then we're going to add our y's, because those are like, and get 2y. So 3 plus 2y is equal to 15. So we're going to do the same as the first addition pyramid, and we're going to subtract the 3 from both sides, and we are going to get 2y is equal to 12. Now our last step would be to separate the 2 from the y, and that is bonded together by multiplication. So we have to do the opposite and unbonded with division. So we would do 2y divided by that 2 and get 12 divided by that 2 to get y is equal to 6. So now that we have our y is equal to 6, we can then determine what our other numbers are going to be. So that would be 1 plus 6 is equal to 7, and 2 plus 6 is equal to 8. And if we wanted to check our work, we could say, okay, 7 and 8 equals 15, and it does, so we would be correct. And for our last equation, for our addition pyramid, we are going to do the same thing that we did for pyramid 2. In pyramid 3, again, we have a variable and we have 2 missing boxes. So it's fair to say 2 plus z is equal to the left-hand box up here. And 9 plus z is equal to this right-hand box. So to equal 27, we would say z plus 2 plus 9 plus z is equal to 27. So let's look at that. We have our z plus 2, we have our z plus 9, and we have it equal to 27. So again, we're going to combine our like whole numbers, which is 9 and 2, so we would get 11, plus 2z, just like we did in the last one, plus 2z. So we're going to subtract our 11 from 27 to get 16. And again, our 2 and our z are bonded by multiplication, so we are going to have to unbond those by division. So 2z z divided by 2 and 16 divided by 2 would get our equation to z is equal to 8. So once we have that information, we can now figure out that 8 plus 2 is equal to 10, and 9 plus 2 is equal to 11. So we can go ahead and do that. Alrighty, so that is function 1. Alright, question 5. 4 married couples belong to a bridge club. The wives' names are Kitty, Sarah, Josie, and Ann. Their husbands' names, in some order, random, are David, Will, Gus, and Floyd. Use the table below to sort out who is married to whom. So we kind of have some hints here to distinguish who is married to whom. Floyd is Josie's brother. Josie and Gus dated some, but then Gus met his present wife. Kitty is married to Will, so we flat out just have an answer that Kitty is married to Will. Ann has 2 brothers, and Ann's husband is an only child. So we can go ahead and establish this with a table. I already have the answers marked in here, but we're just going to go through it together. So, the first one is Floyd is Josie's brother. So we can go ahead and go to Josie and mark out Floyd with an X because they are brothers and sisters, so they're not married. Josie and Gus dated some, but then Gus met his present wife. So again, on Josie, we can go ahead and mark out Gus as well, which is on the bottom, covered up by the presentation toolbar. So we can go ahead and mark an X for Gus as well. So the only options left for Josie would be Will and David at this point. Well, then it straight up says Kitty is married to Will. So we can go ahead and mark out Will from Josie's column, and that leaves her with David. And for Kitty, we can go ahead and mark everyone out except Will because it says straight out that Kitty is married to Will. So we know that Josie at this point is married to David, and Kitty is married to Will. Because Josie had no other options left, so she must be married to David. And it straight says that Kitty is married to Will. So for Sarah and Ann, it says that Ann has 2 brothers. Well, doesn't really tell us anything right off the bat, but yeah. Ann's husband is an only child. So that would mean that, which Ann's only 2 uncles at this point are Floyd and Gus. Well, if Floyd is Josie's brother and Ann's husband is an only child, that would mean that Floyd is not an only child, and she would be married to Gus, and that would leave Sarah with Floyd. So that is how we would do that, and that is using inductive language. Okay, question 6. Consider the trapezoidal numbers 1 plus 1 plus 1, 1 plus 2 plus 2 plus 2 plus 1, 1 plus 2 plus 3 plus 3 plus 3 plus 2 plus 1, etc. The nth trapezoidal number is 1 plus 2 plus etc. plus n plus n plus n, etc. Where n is a positive integer. So here is asking us to choose which of the, create the trapezoidal numbers. And here we would do that, so 1 plus 1 plus 1 equals 3. So we would start out in just a single file line because it's asking us to create a trapezoidal shape. So for the next one, 1 plus 2 plus 2 plus 2 plus 1, we would go ahead and add that other layer because that is equal to 8. So we have 8 in this next trapezoid. So in this next trapezoid, we have our original 8 here, 9, 10, 11, 12, 13, 14, and 15. Alright, and then we have our original 15 plus another 1, 2, 3, 4, 5, 6, 7, 8, 9. So 15 plus 9, 5, that is 24. So we have established our trapezoidal shapes. Then it is going to ask us to create, if we are able to create it in a rectangular shape, which we are. We have our original 3, so I'm just going to write this here. We have our original 3, and then we go ahead and arrange our next 8 into 2 rows and 4 columns. And the next one we can do 3 rows and 5 columns, and then 6 columns and 4 rows. And the equation for this with our positive integer number is n and n plus. Alright, so that is all for Module 1, Critical Thinking. I hope you learned and you enjoyed, and I will see you in the next one.